where we've got to is that we all should have a good appreciation now for the fact that our soil in New Zealand, the soil surfaces in New Zealand have a net negative charge. Okay? You all should be convinced of that now, and you should all be happy with the fact that our soils have charge, and it is a negative charge. And more importantly, it is a net negative charge. So there is a little bit of positive charge, but the negative charge is the dominant charge. Now there are two mechanisms by which we can get charge in soils. Who can remind me what those are? Two mechanisms. Firstly, there is, begins with P, permanent charge. Okay, you need to remember these things. You should be starting to fire them out now. Okay, firstly we have permanent charge. And what's the other one?
Variable.
Cool, we've got variable charge. Now there is a particular soil component that we associate with permanent charge. Remember, we have three key components of our soil system. Which of those components is associated with permanent charge?
Colloids?
They're all colloids, because colloid really just refers down to the small particle size. But remember, there are three types of those colloids. Remember, what's the one that we get, that starts off as a rock and then it breaks down, and the permanent charge that was in the rock through isomorphous substitution carries on to the soil. So it's
Clay silicates.
clay silicates. Cool. So permanent charge is associated, doing too well with my pens here. Permanent charge is associated with clay silicates. Great. Now what is associated, or what component of the soil has variable charge? Okay, we've got rid of clay silicates, that's two of the three gone. The other one is
Organic matter?
organic matter. Great. Okay, so we have organic matter. And that's what we've been discussing over the last couple of lectures. Remember that organic matter has terminal functional groups that stick off the end of the organic matter surface. And what happens is that those terminal functional groups can protonate or deprotonate. If it's acidic, they can gain acid. If it's alkaline or less acidic, they'll lose H pluses and become negatively charged. Now there's one other component, isn't there? And what's that other third component? Rust. Okay, what's the complex word for rust? We were talking about it this morning at 9 o'clock. It's
Oxides.
oxides, cool. So oxides, hydrous oxides of
Iron and aluminum.
iron and aluminium. Okay, cool. Iron, aluminium, hydrous oxides. It's called hydroxides. Right, so those are the three key components. You've got to remember those three things. So this part of the course, this chemistry section, is all about these three things: clay silicates, organic matter, and iron and aluminium hydrous oxides. They're the colloids because they have small particle size, large surface area, they're reactive, they provide surfaces on which our chemistry can occur. Remember, each of those three things accounts for this part of our little wee model. Nutrients in soil solution, three things can happen. What?
Uptake.
Uptake by plants, react with the soil surface, or leach. And we don't want that. Okay, so there's our soil made up of those guys. We know because of that, because of the permanent charge and the variable charge, it's got a net negative charge. So in soil solution, where we have our ions, things like calcium ions, sodium ions, potassium ions, and magnesium ions, okay, those are our cations, our base cations. Then we have our anions, we have phosphate, we have sulfate, and we have nitrate. Okay, those are our soup of ions in soil solution. Those are the forms of those nutrients that plants will take up. So we know that the cations will be attracted to the surface. Okay, calcium 2+ will take up 2 negatives, so magnesium 2+ will take up 2 negatives, potassium takes up a negative, and sodium takes up a negative. Okay, so there's our non-specific electrostatic interaction. We call that non-specific adsorption. Okay, so there we go. So we know now that our soil will retain our cations, and we should all be confident about how that happens. Now, as a result, we also can see that the soil, based on this rule, based on this electrostatic mechanism of non-specific adsorption, we can see the soil is going to repel sulfate, it's going to repel nitrate, and it's going to repel phosphate. And so theoretically, based on that model, those three nutrients are going to leach. Retain the cations and repel the anions. And that follows through, and that's what we see for this guy. Because all through the media we hear about nitrate leaching. Farmers have problems with nitrate leaching because they get in trouble with regional councils. Okay? It's not good for the bank balance because that's our money going down the plug hole basically. So nitrate leaches because it can't be retained by the soil. Nitrate's negatively charged, the soil's negatively charged, it will be repelled. So we put nitrate into soil solution, plant uptake, some of it will go into the plant. The action with the soil is actually repulsion, okay, so it's not going to be retained on the soil, so that one's out, so it will leach. But do we hear about this guy leaching? Who can say they've heard of a story of phosphate leaching through soil? Anybody? So what do we hear about phosphate doing?
Road.
It erodes. Yeah, we do. We hear about phosphate erosion. What happens is the phosphate gets lost with the soil as the soil erodes off the surface. So clearly there's something else going on. And that's what we talked about in lecture this morning. What's actually going on here is we have another mechanism. We have the potential for phosphate to specifically adsorb, and that's what we're going to investigate in this lab. Now, we'll just briefly touch on the fact that we've got these three components in soil, okay? And so what will contribute these components to the soil is the pedogenesis, okay? What makes up the soil? So for today's lab, we're going to be passing phosphate, a solution with phosphate, nitrate and sulfate through two different soils, okay? And that's what's in front of you now. We've got a soil column with some Tokomaru soil. Okay, it's a Tokomaru silt loam, and this is from around the Manawatu, and we've also got a Egmont silt loam. Two different types of soil, and as you can imagine, those two different soils are formed from two different original sources. If we think about Egmont, what's the big hunk of rock that's in Taranaki that you think is going to contribute to soils? What's the biggest hunk of rock in Taranaki?
Mount Taranaki.
Yeah, Mount Taranaki, cool. So, this here is going to have clay silicates, right, because all soils have clay silicates. It's going to have organic matter, because all soils have organic matter, but it's also going to have iron and aluminium hydroxide because it has an input from volcanic activity. And this stuff can also be called allophane, comes from volcanic events. Now what makes up the Tokomaru? What's around here? What's a big hunk of rock around Palmerston North that you think is going to break down and make soil? We haven't got a volcano. Well, we have, but it's a bit further away. Ruapehu's a fair way away. But what have we got that's very close by? We've got the ranges. Cool. We've got the Tararua, the Ruahine ranges. Now they're primarily grey-wacky. Okay? So they're metamorphosed rocks. So it's old sedimentary rocks being compressed and uplifted. So they are going to break down and they're going to give us clay silicates and we're going to develop organic matter. But we're not going to have nearly as much iron and aluminium hydroxide. We'll have some because we get some volcanic activity from Ruapehu that blows this way. So there'll be some influence of iron and aluminium hydroxide, but nowhere near as much in the Tokomaru soil as we find in the Egmont soil. So what we're going to do today is we're going to do an experiment. We're going to pass our nutrient solution through these two different soils and see how the soils respond. that's probably enough for that, Jean.
Sure.
So what I'll do for the next part